Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 11 of chapter 1, that is transformers. So today we will discuss about the assignment solutions and the equivalent circuit of multiple winding transformer. We have not drawn the equivalent circuit for multiple winding transformer, that also will draw. Okay. So this is the first question. This was a GATE 2003 question. Figure shows an ideal single phase transformer. The primary and secondary coils are shown. Turns ratio is this. The correct phasor for E1, E2, I1, I2 and the core flux phi will be equals to what? Okay. What will be the correct phasor? So here, right, if you remember one thing, that like our phasor of ideal transformer was something like this. V1 was here. V1 was here. Then I had E2 and E1 here. And then I had this flux here, right? This was actually the ideal transformer uh, voltage. But here instead of E1, I had V1 here, right? I had V1 here. But actually this time, right, what they are doing, they have just changed the name. So E1 was supposed to be my induced voltage, but here E1 is the supply and E2 is the induced voltage, right? And they have not named any induced voltage, so that is not included in the phasor diagram. So this will be my V1, right? That is E1 in this case, in this question, and phi will obviously lag the E1 by 90 degrees, and E2 will be in phase opposition with actual supply voltage E1, and it is a resistive circuit. So of course my current will be in phase, my I2 current will be in phase with the E2, my I1 current will be it, as it is a resistive circuit. Here also some resistance equivalent. If I refer this resistance to the primary, I will have a resistance only. The value will be different, but I will have a actually resistance only. So if it's a resistance, the current will be in phase with E1. Okay, so option D will be correct. So it is the same whatever we have learned, phasor diagram, whatever we have learned, the same only. The difference is the just that they have changed the name from E1 to V1. Sorry, they have changed the name from V1 to E1. That's it. Also, you can understand it like this: is my I2 is here, what will be my I2 dash? So I will, okay, I will not edit this one. Okay, I will copy this. What will be my I2 dash? I2 dash will be just opposite of I2. So this I1 is actually is the opposite of I2. That's it. I2 dash they have not obviously not named here because that is not present in the circuit. I1 is present. Okay, so that's why option D will be the correct answer of this particular question. Very simple, very easy question. Okay, now let's solve this question. This question is again very interesting. We have this 400, 200 volt, 200 volt, 50 hertz, 3 winding transformer. So here this is 400 volt, so this has 400 turns. This particular coil, this coil has 200 turns, this coil has 200 turns. So if I apply 400 volts across these coils, then I will receive 200 volts here and 200 volts here. Okay, 50 hertz 3 winding transformer is connected as shown in the figure. The reading of the voltmeter V will be, what will be the reading of the voltmeter V? Okay, what will be the reading of the voltmeter V? So they are asking me what will be the reading of the voltmeter V. So let's assume this voltage as what? Let's assume this voltage as some V1. Okay, so what is V1? V1 is just, if I just apply the KVL, V1 will be 400 volts. Okay, V1 will be 400 volts. Everything is in RMS. Okay, everything is in RMS. Now, as this is a transformer, so the voltage induced in this coil will be what? Voltage induced in this coil will be 200, right? So this will be the voltage here, that is V2. V2 will be 200, correct? According to the turns ratio. What will be the voltage induced here? Voltage induced here will be 200, but remember the polarities. This is dot, this is dot, this is dot. So this will be at higher potential. So the direction will be something like this. V3 will be 200 volts, but make sure you are writing the proper direction. So this will be plus, this will be minus, this will be 200 volts. Okay, and I have to measure the voltage between these two points. So let me write down the points. Let me do one thing. Let me just simply do a KVL. So this is the voltmeter reading. Let's assume this is the voltmeter reading Vm. Okay, so I will apply a simple KVL. I will follow a loop. So I will copy this diagram. What I will do, I will copy this whole thing. I will don't want to mess up the actual question. So this, all these things can be deleted over here. So basically I can simply apply a KVL like this. So I will start from, let's assume I will start from this point. Okay, I start from this point, start from here, here, I go here, then okay, this will not actually be a loop, this will not be a loop, oh, this will be a loop, right? This will be a loop. Okay, so basically what will the voltmeter read? So this is actually a loop. Is this a correct loop? That is what I'm thinking of. No, no, no. What am I doing? I cannot go from here to here, right? This is not connected electrically. So I have to follow a electrical loop. So I'm sorry. So I'll start from here. I have to electrically follow, right? I have to go here, go along this winding. Okay, this is. I will start from here, go along this wire, along this wire, along this wire, along this. Now I finish the loop. So I have to go along the wire, right? Like I have for KVL to follow, I have to follow a loop, follow the electrical loop. So this is minus plus 200. Polarities are sorted because dot is with plus, because here dot is with plus. So I hope I don't have to explain polarities. We have covered enough questions on polarities. So this will be again, this is dot, so this will be plus minus 200 volts here. Okay, and this will be plus minus 400 volts here. So now I will apply KVL. My KVL is, I write whatever value I encounter, I write the first sign. Okay, so I will write minus Vm. You can follow according to your notation. Minus Vm, minus 200, then minus 200, because here also I am encountering a negative sign first. As I am going along this loop, first I am encountering a negative sign here, then again I am encountering a negative sign here, then again here I am encountering a positive sign. So this will be plus 400 equals to 0. So my Vm actually comes out to be 0 volts. Very interestingly, Vm comes out to be 0 volts. So the voltmeter will actually read 0. Okay, so and this is a gate question. I guess this is a gate question. So they will ask you questions in dot convention. That's why we covered it so comprehensively. They will ask you basic questions and you will not be able to solve it. Okay, so just be careful regarding all this. Now let's come to the next question. So this is the next question. A single phase transformer has a turns ratio of 1:2. So this is 1:2, is connected to a purely resistive load as shown in the figure. The magnetizing current is 1 ampere. The secondary current is 1. If the core and leakage reactance are neglected, the primary current. So primary current, right, is a combination of the no load current plus the I2 dash current. So what is no load current? No load current, remember, they have told me that the core does not have any losses. So no load current will be is equals to IC plus IM, if you remember, and this time IC 0 because there are no losses in the core. So this will be IM only, and I know IM is proportional to flux, so it actually lags the voltage. So the phase will be magnitude of IM angle minus 90 if voltage is assumed to be reference. Okay, just be careful regarding this. So IO will be magnitude of IM, and they have told me the magnetizing current is 1 ampere, so it will be 1 angle of minus 90. What is I2 dash? So I2 dash, it is a purely resistive circuit. So here this is my V1 voltage, so this is V1 as well, so this will be my V2. So V1 V2 are basically so this is V1, right? So this is E1, okay, this is E2 and this is V2. Okay, so V1 E2 equals to V2, right? So my phasor will be somewhere here, right? Phasor will be some, like this is my flux phi not that, okay, sorry if you heard something else, I'm sorry, I meant flux. So this will be E2 E1, okay, and this will be here, this will be my V1 basically, right? And V2 will also be here only because my I2 is in the same direction because it is a purely resistive circuit. So what will be I2 dash? I2 dash will be actually in phase with the voltage V1. So it is in phase with the voltage V1. So I2 dash will be in phase with the voltage V1 because it is opposition. So assumption is my reference is the input voltage. So it is V angle 0. Okay, that is my assumption. So according to the reference, what is the phase difference between I2 dash? 0 phase difference. So this will be, they told me the secondary current is 1 ampere, but I have to refer it to the primary, so it will be N2 divided by N1, correct? N2 divided by N1, so it will be 2 divided by 1, okay, and angle will be 0. So this comes out, so my I1 comes out to be minus J plus 2, okay. So if I just, they have just asked us the the primary current, basically the magnitude, they are not asking the phase. Actually the phase, right? They have not asked us the phase. So magnitude will be 1 2 square plus, that is under root 5. So under root 5 will be 2.236, 2.236 amperes. Okay, and what will be the phase angle? One divided by 2 tan inverse, okay, not this, 1 divided by 2 tan inverse, so minus 26.56. But of course they have just asked us the magnitude, so it is 2.24. 2.24 will be the correct answer of this particular question. Pretty simple, not that difficult to understand. Okay, let's move on to the next question. So a large transformer under no load condition uh, is operating. Okay, operating under no load condition. So there is like the secondary current is simply 0. The secondary current is simply 0. So only no load current is taking, that is known as no load exciting current, that is 5 ampere. So IO is equals to 5 ampere. When its primary winding is connected to 120 volt and 60 hertz supply, the wattmeter test indicates that iron losses amount to 180 watts. Okay, so this is actually we have still yet to discuss about iron losses. So this whatever losses happen in the no load, right, are actually known as the iron losses. We will discuss about this later on. For now, what your task is, they have told you the iron loss. This roughly I have discussed that iron loss is known as the coal loss, that is given as 120 watt. Where actually this happens? So if you remember the model of the transformer, I had this model, right? If I neglect the winding resistance for now, so the model was somewhat like this. This was my RM core resistance, and this is my JXM. Okay, so this will be my V1 basically, and this will be my E1, induced EMF. So I hope you remember, right, where actually the losses happen. Losses happen here. So what is the loss equals to? I had previously discussed the loss. P core loss will be the wattful component that happens in the RM, that is equals to V1 square divided by RM, if you remember. So this value they have given me actually, that is 120 watts. And they have also told me that the no load current is 5 amperes. This no load current is 5 amperes. So some of it will be used for the magnetizing component and the other will be used for the wattful component. Also they have given me the RMS value of the voltage. So from this RMS value of the voltage, this is my V1, that is 120 volt. I can easily find out the RM. And they have asked the reactive power. I will be able to find out the reactive power. I will tell you how to find out the reactive power. So this will be equals to basically V1, that is 120 whole square divided by RM, that will be equals to 120. So my RM actually is equals to 120 ohms. So RM is 120 ohms and the no load current is 5 amperes. So how do I find out actually the XM? How do I find out the XM? So there are many ways to solve this question. Okay, XM you can find it out like this as well, that RM I have find out that sorry, you have to find out the reactive component of the power. How do I find out the reactive component of the power? So one thing I know, that this V1 into IO is the overall kVA or the S of the this equivalent resistance. This much I know. Okay, now I know that the P core is the active power loss present in the this combination, correct? So I hope you have studied complex power. So I will use bit of complex power. If you remember my power factor angle cos phi 0, what will be the power factor angle cos phi 0 for this particular component? Because I am only talking about this component because it is no load. So here the current is 0 ampere. So whatever current is coming, that will totally go in this particular circuit. So cos phi 0, if you remember, it was active power upon the apparent power. So it is P core upon S naught. Apparent power of this particular circuit only. Okay, I am only discussing about this circuit. So P core is actually equals to what is P core equals to? P core is equals to 120 watt that we have calculated, and S, right, is equals to V1 into IO. V1 is 120, IO is 5. So actually my cos phi O is equals to 0.2. Cos phi O is equals to 0.2. Okay, this is what my cos phi O is equals to. Okay, so now they have asked the reactive component of the power. What will be the reactive component? So reactive component of the power will be equals to sin phi O. So sin phi will be equals to this, right? I'm just using complex power. Okay, I'm not using anything else. I'm just using complex power. So my sin phi O will actually be equals to, am I correct? This is the active power component. Reactive power component will be VO into, just I'm thinking something else. This is the kVA loss, and there is two components to it. Yeah, this is actually correct only. Yeah, so sin phi O will be equals to my reactive power in the core divided by the overall S naught. So from here, right, I can easily find out my phi O. Okay, so this will be 20, S naught is 120, so this will be 0.2 cos inverse, so 78.46 degrees. Okay, so Q core will be equals to, they have asked me to find out the Q core, right, the reactive power consumed in the core. It will be S naught into sin phi naught. So S naught is V into I, that is 120 into 5, and it is 5 amperes, right? Yeah, and my sin phi naught will be what? It will be 78.46, sine of 78.46, so it will be 0.98. So into 120 into 5, so this will come out to be 587.87 VAR. Okay, volt ampere reactive. So this is what the reactive component of the power will come out to be. Okay, just quickly want to check one thing. 78.46 to sine, yeah, it's 0.9. Okay, so they have also asked us to find out the core resistance that I have already found out here with the core loss. This is already found out, and this is the A point, and the other one, and the magnetizing reactance. What will be the magnetizing reactance? So magnetizing reactance is actually pretty easy. Magnetizing reactance will be equals to the basically xm will be equals to the voltage divided by the magnetizing current, right? Magnitude of the voltage divided by magnitude of the current. Okay, I don't know what is Im, right? I don't know what is Im. So right, if you remember that here I had my phi, this was my Im, this was my IO, so this was my IC, and this was my IO, the addition of these two, correct? So this was my phi naught, if you remember. Okay, so from here also you can find out. So my Im will be equals to what? IO sin phi naught. My IC will be equals to what? IO cos phi naught. Okay, I'm just thinking if I'm making any mistake or not. Cos this, okay, yeah, I guess, yeah, it is fine only. So Im, I know sin phi naught is 0.98, and IO is 5 into 0.98. Okay, so into 5, so this will be 4.9 amperes. This will be 4.9 amperes. Okay, this will be my Im. This will be my Im. I know magnetizing current, I know voltage is 120 only, so this will be 120 divided by 120 divided by 4.9 amperes. Okay, so from here I can easily find out the magnetizing reactance, so it will be 4.495 ohms. So this will be my magnetizing reactance, basically 24.495. This will be the answer. Okay, so we have solved this question. So like this also you can solve, like there are n number of ways, because we have already solved phasor diagram, we have already done phasor diagram. So circuit analysis you can do, I'm leaving it up to you, I'm not explaining here because this is difficult. Yes, transformer you don't know, so I have converted into circuit, so then it's up to you, right? After I convert this into circuit, then it's up to you, because you have already learned network theory from me, AC analysis. So that's why AC analysis is very important. Okay, so let's now move on to the next portion, next question. So this is the next question. So here a single phase transformer is supplied with a fixed sinusoidal voltage, okay, at its primary. This is the primary, this is the secondary, while the secondary remains open circuited. Okay, if a portion of the iron core shaded region is removed, how will the parameters be affected? The exciting current magnitude. Okay, what will happen to the exciting current magnitude? So what do I know? That if I apply a voltage, right, in the primary, if I apply a fixed sinusoidal voltage, so that means if I am applying a fixed sinusoidal voltage, so it is, let's say, some V1 of t is equals to Vm1 sine omega t. Okay, so here, right, the voltage, peak value of the voltage gets fixed, the frequency of the voltage gets fixed, and of course this core, right, I will not change the number of turns, so number of turns is also fixed. And what did I tell you? If all of these are fixed, then my peak value of the flux will also be fixed. So phi m is fixed. Now if phi m is fixed, what is phi m equals to? Phi m is equals to mmf upon reluctance. So this, right, will be equals to n1 into Im divided by reluctance. Now they have told me that I have removed the one of the portion of the core, iron portion, and if I have removed, then basically there is air, right? It is air. If it is air, you know, it is like a series magnetic circuit. Okay, if I have removed this, then here I have air. That basically means that this portion will have very low permeability. If this portion has very low permeability, that means what? That means my overall, like, it is a series circuit, right? So here I am applying a mmf I am applying, that is n1 into Im. Okay, and here I have the S core reluctance. If I have removed this, right, so slightly the core reluctance will reduce, this side, slightly this core reluctance will reduce, and but a huge reluctance will come, that is the air gap reluctance, and you know air gap reluctance is very high. Okay, I will not discuss why, all this has been covered previously. Then of course I know that my phi m will be fixed, my phi m is fixed. So phi m is fixed, right? Phi m is fixed, but overall my reluctance, actually overall reluctance of the circuit increased. That means what? That means I have to increase my mmf, but my n1 is fixed, so I have to increase my Im. So if Im increases, what is IO equals to? Exciting current. IO is equals to IC plus Im. So if Im increases, of course IO will increase, the no load exciting current will increase. So for generating the same amount of flux, I have to apply more current. It makes sense, right? Because the reluctance has increased, because I am inserting air. It is not a iron material. Iron is very good magnetic material, but I am inserting air. If I am inserting air, that means I have to work more harder to flow the same amount of flux, because air has low permeability. So the exciting current increases. So exciting current will increase. So first two options is correct. Can be correct options. Let's read the next one. Core flux. Core flux remains constant. Already discussed, right? Core flux will not change. Core flux will be constant. Okay. So if core flux is constant, so only option A will be correct. Let's read the last one. No load power factor. So what will happen to the no load power factor? So if you remember, your exciting current is a combination of the magnetizing current and the, here I have flux. It is a combination of the magnetizing current and the core loss component of the current. So initially let's assume I had this Im, right? And this is my core loss component of the current, IC. Okay. But In the case 2, what will happen? Once I will remove that iron portion, shaded portion, the magnetizing component of the current actually has to increase to produce the same amount of flux. But core loss component will not change, because what does core loss component depend on? It depends on V1 by R1. So voltage I'm not changing. R1 core resistance of the core will not change much. It will change, but very small amount. It will change very small amount. So it will not change much. So IC will be this much only. IC will not change. So if you see, initially what was my IO? So initially my IO was here. Okay. Next time what is happening? Next time my IO is here, that is IO dash. So my IO is actually here. So what is happening? What is the phi naught angle? Phi naught angle is with respect to IC, right? If you remember, it was the no load power factor that was with respect to IC always, because V1 also was in the same direction only. V1 also was in the same direction only, if you remember, right? So my phi O, initially this was the initial phi O, and phi O dash is here. So of course phi O dash increases. So phi O increases. If phi O increases, the power factor will reduce, right? Phi O has increased, so cos of phi O will reduce, right? Cos theta and theta follows inverse relationship. So if theta has increased, cos theta will reduce. So no load power factor will reduce. It will worsen. Worsen means, of course, we don't like in power systems we will learn this, that there is a term known as power factor correction. So we want to be as close to unity power factor as possible. Okay, we will learn this in power factor. So here, that's as cos phi is reducing, so it is going further away from UPF, away from unity power factor. That is not a good sign. That's why it is telling that it is worsens. So that's why option A will be the correct answer in this question. Okay, so yeah, now let's move on to the next question. So this is the next question. Like whatever we have learned, we are just implementing those concepts. So here in the figure, they have told me that I have a load that absorbs 4 kilowatt of power at 0.89 lagging. Assuming the transformer to be ideal, the value of the reactance X to improve the input power factor to unity. What should be the value of X so that I can improve the power factor to unity? So let me draw the equivalent circuit here. Okay, let me draw the equivalent circuit. So I will refer this load here. If I refer this load here, can you tell me which one of these components will change in the primary? If your answer was power, then I will come out of the screen and totally slap you. Okay, because I have always told you that the power always remains conserved in the primary and secondary. It will not change. So this will be same. If I refer it to the primary or secondary, the power consumed by any load or source will be same. It will not change. The power factor also does not change, because we have not discussed about power factor. What is power factor? Power factor is basically the ratio of R by Z or something. Ratio of two impedances, right? If it is a series circuit, if it is an equivalent series RL circuit or RC circuit, it will be ratio of R by Z. So basically, if I am referring to the primary, then R is also getting scaled by N1 divided by N2 whole square, and Z also will be scaled by N1 divided by N2 whole square. So both of them are scaled by N1 divided by N2 whole square. So what is happening? They are cancelling each other out. So the power factor also will not be changed in the primary. Okay, if I refer it to the primary. Okay, understood? Now let me draw the equivalent circuit. So if I draw the equivalent circuit, here I have the input source. Okay, here I have the input source, and here I have this resistance, that is 1 ohms, and I have to place a reactance. They are asking me the value of the reactance. What will be the value of the reactance to improve the power factor? So they are asking me what will be the value of the reactance. So how to improve the power factor, we will discuss. So generally it is like a power system question, but here also we can understand. So this is X actually, and here I have this load. This load is there, ZL, that takes how much amount of power? 4 kilowatt of power at cos phi 0.89 lagging. Okay, so I have to improve this power factor to unity. How will I improve the power factor? So basically, right, I want unity power factor. If I want unity power factor, that means whatever power this source will supply, it will be purely wattful component. There will not be purely active. So only, so the source will supply apparent power, that will be Pin or PS plus JQS. But actually I don't want that. I don't want the source to supply QS. I want whatever reactive power this load requires, that will be supplied by this X. Okay, that should be supplied by the X. How will it supply? So here, right, what you have to understand, what is the reactive power that this load is taking. So my active power is 4 kilowatt, cos phi is this. So what is the apparent power of this load? It will be like Vi cos phi. So sorry, not apparent power, sorry, the active power is this P equals to S cos phi, right? S cos phi. So I can, from here I can directly say what is my apparent power. Apparent power will be 4 kilowatt divided by 0.89. But I don't want this apparent power. I want the reactive component of the power. So reactive component of the power I know is S sin phi. All these I have taught in the AC part of the networks. So I hope you have watched those videos. So sin phi. This is L, right? Sin phi L, cos phi L, all these are L. So this will be equals to, so apparent power is 4 by 0.89 and sin phi, right? Cos phi L is 8.89. So easily I can find out the sin phi L. So 0.89 cos of inverse, this will be 20. So phi L angle will be 27.126 degrees. So sine of this, right? Sine of this angle will be 0.456 into 0.456. Okay. So my I can directly write here this into 4 divided by 0.89. This will be equals to 2.05. Q will be equals to 2.05. This will be kVAR. Okay, so this much amount of reactive power I want this X to supply, instead of this input source to supply. I want this X to supply this much amount of power. Okay, so what is another thing? This is the voltage source. Okay, they have actually, okay, this voltage is 110 volts. This voltage is 110 volts at this point. So if I refer it at this point, what will be the voltage? If I refer it here, what will be the voltage? It is 2:1 transformer, so it will be 220 volts. So across this, right, I have 220 volts. Okay, across this I have 220 volts. So I can directly write what will be the, basically there is no other reactive component. Basically this X is actually a capacitor. One thing I wanted to say here, actually they should have mentioned that they are asking the magnitude of the reactance, because it will be a capacitive reactance, so actually it should be minus of Xc, but at that point of time they have not figured out. So I mean they have figured out, but they actually maybe they have not thought about it, that many students may get confused that capacitive reactance is negative, so they might answer here negative. They actually should have written magnitude of the reactance, right? That would have been the correct term. So the voltage is 220, right? This point voltage is 110. So this point voltage will be 210. Remember, one mistake you can do, if this is dot, basically this point will come here and this point will go here. But as it is an impedance, it does not matter. If I connect it upside down, if I flip it, it does not matter. Okay, it does not matter. Power consumed will be still be same. Okay, so this much amount of reactive power this reactance need to send. So what is the reactive power of this reactance? How do I calculate? So reactive power, all these I have taught you in AC analysis. So please, fundamentals is very, very important. So reactive power supplied by the this X reactance, right? It will be V square divided by X. All these I have taught you. Okay, it's not like I have not taught you. All these I have taught in the AC analysis. So I will write here directly. I will not explain anything here. Okay, so this V square by X. So V is 220 whole square, all these are RMS values only, divided by x. This is what I have to find out. This is not the active power, sorry, reactive power. So this will be equals to the reactive power that I need to supply, because the whole reactive power will be supplied by this capacitive reactance, and supply will only the actual source will only supply the active power, okay, which I don't care right now. So this is equals to 2.05 into 10 cube. So this will be basically 220 whole square divided by x into 10 cube. Okay, so this will be 220 whole square divided by 2.05 divided by 1000. So x will be equals to 23.6 ohms. This is the value. Basically they have asked this. Actually it is a capacitive reactor, so there will be a negative sign, but this will be answer. Basically they should have asked the magnitude of the reactance. Okay, so this will be the answer for this particular question. Very good question. This can actually be solved in power system as well, in here as well. Okay, there we learn about power factor improvement. Okay, so let's now move on to this next question. Next question is like, this is pretty bit. I think this is a very latest question. Well, this is like GATE 2024 or GATE 2023 something question, right? So here, when the winding CD of a single phase 50 hertz transformer, two winding transformer, is supplied with the AC current, okay, the rated voltage I am getting at the primary, okay, it is open circuited, okay, the cross sectional area of the core is 5000 mm square. Okay, so let me write down few things. So A is 5000 mm square, okay, my length, so the average core length traversed by the mutual flux that is linking both the primary and the secondary is 500. So L is equals to 500 millimeter. Okay, then the maximum allowable flux density in the core is B max is 1 Weber per meter square. Okay, the relative permeability of the core is 5000. So mu r is 5000. Now the leakage impedance of the winding AB and winding CD are this. Okay, so winding AB leakage impedance, leakage impedance and the winding resistance both are combined here. So basically my Z1 is equals to this 5 plus J 100, basically omega 2 pi f into the inductance value, leakage inductance value, and Z2 is equals to 11.25 plus J 100 pi into 0.36. Okay, this is my Z2 basically. This is my Z2. So considering the magnetizing characteristics to be linear and neglecting core loss. So magnetizing characteristics is linear, that means it will never saturate, core will never saturate. The self inductance of the winding AB in millihenry is, what will be the self inductance of the winding AB? So basically, right, we have to find out the self inductance. So how do you find out the self inductance? So if you remember, we had a formula. Self inductance formula was equals to N square by reluctance. N square by reluctance. But this time the reluctance is quite different. Right? It is like a parallel circuit. Okay, it is like a parallel circuit because I have number of turns here, but there are two reluctance. One is the air gap reluctance, that is the leakage reluctance. Other one is the core reluctance. Right? So it is a parallel circuit. So basically I can write here that my overall reluctance 1 by S will be parallel combination of the core reluctance plus the air gap reluctance. Right? S air gap, due to which the leakage flux will flow basically to the air gap, right? So if I multiply on n square n square on both sides, right? If I multiply n square on both sides, so this will be n square by s will be equals to n square by s square, s core plus n square divided by s air. So one thing is there that they had already told me what is the inductance like of the air gap, leakage inductance of the air gap here. It is already told to me, that is it is 0.16. They have already told me, right? So I already know this value. So basically, right, my L, overall L will be equals to L of the core inductance due to the core plus the inductance of the leakage flux. So leakage flux inductance is already given to me, right? Because this is 2 pi f, that is 2 into 50, that is 100 into pi, and this is L, omega L basically. So this is my L, leakage reactance, right? So this is already known to me, that is 0.16. I just need to find out the inductance due to the core. Okay. So how will I find out the inductance due to the core? Very simple. I have to find out n square by s. So s is what? S is simply L upon mu A, right? I know L, I know A is known to me, mu is also known, mu naught into mu r. What is not known to me? N. Number of turns actually they have not given to me. So I have to use some other equation. So another equation I know that my voltage V1 RMS is equals to root 2 pi f phi m into n1. So from here actually I can find out the value of n1. So but phi m is not given to me, but bm is given to me. So what is bm equals to? Bmax, bm or bmax is equals to phi m into area basically my uh, uh, no what I'm doing, sorry my phi max is equals to bm into area, because bm is phi max divided by area. I will replace everything. So I know my V1 RMS. V1 RMS is given to me, that is 200 volts here. So this will be 200 volts. This will be 200 volts here. This will be equals to root 2 into pi into f. F is 50 into phi m. Phi m will be bm into a. So what is bm? Bm is given as 1 Weber per meter square. So it will be 1 Weber per meter square into the area. Area is given as 5000 millimeter square. 5000 millimeter square. So it is 5000 millimeter square. In meter square it will be 5000 into 10 raised to power minus 6. And n1 obviously I have to find out. Okay. So this is my n1 value. So if I want to find out what is n1 actually, what is n1 equals to? So n1 will be equals to, I have to calculate this. This will be a bit hectic. So this will be 4, and this 5000 will be 5 into 10 raised to power minus 3. So this will be 10 cube divided by 5. 1 will be staying there, it will be root 2. Okay, that's it. So this value, right, this value n1 will be equals to 10 cube divided by 5 divided by root 2. So this will be 100 root 2, that is 141. Oh sorry, there is a pi, right? There is also a pi here, don't forget the pi. Okay, so the pi is here, so divide by pi as well. So this will be 45.01. So approximately, of course number of turns cannot be like fractional, so approximately it will be equals to 45. Okay, so what will be the inductance? It will be, what is the L core, right? L core, it will be n1 square divided by reluctance. So n1 square is 45 whole square. What is the reluctance? Reluctance is L by mu A. So L is what? Basically L is, they've given me L as 500 millimeter and mu is 5000. So 500 so mu is mu naught into mu r, right? So it will be mu naught, that is 4.2 10 raised to power minus 7 into mu r will be 5000. Okay, into yeah, this is mu r into L. Sorry, this will be 1 by, right? So this will be in the inverse. This will not be here. Basically, it is simply L by mu a. That is what I am doing. So L is how much? L is 500 milli. So it will be 500 into 10 raised to power minus 3 divided by A. A is 5000 meter square. So it will be 10 raised to power minus 6. Okay. So my L core will be equals to 45 whole square, and this will go on the top. So okay, bit difficult. Okay, so 10 raised to power, this is 10 raised to power 6, so 10 raised to power 6 actually goes over here, right? Automatically cancels out. This is 10 raised to power minus 7, so this will go at the top, and 10 raised to power minus 3 also go at the top. So this is 45 whole square, and this is 10 raised to power actually minus 1. Okay, so 10 raised to power, this will be 10 raised to power minus 6 into 4 pi into 25 divided by 5 into 10 raised to power, okay, 10 raised to power minus 6, right? That is already taken care of, right? Yeah, that is already taken care of. This 10 raised to power minus 1 actually goes at the top to take care of this, already taken care of. So this is 5 only. Okay, so this will be like this will cancel out, so this will be 5. So here, right, what will be the value? So this will be 45 whole square into 4 into pi into 5, okay, into 10 raised to power minus 6. This will be 0.127 Henry. Okay, so this is 0.127 Henry. Am I correct here? Maybe I'm making a mistake. What mistake I'm making? That is what I'm trying to think, because this answer is not matching. Okay, 45 whole square. So this is 4 pi. Okay, 5000 is the L upon mu. Mu r is this, mu naught, mu r. 4 pi into 10 raised to power minus 7. Yes, this is correct. Okay, this is, yeah, this is 0.5 only. This is also correct. And the n square is, okay, something I've made a mistake in the n square actually. Made a mistake here. Okay, I've made a mistake here. Like my n1 is wrong. It should come out to be 180. So what kind of mistake am I making? So right, this is VRMS, right? This is VRMS. Okay. Yeah, VRMS is this only, so it should be correct only. This value, right? This is 10 raised to power minus 3. This will go at the top. 5 will be here. Root 2 will be here. Pi will be here. Yes. Okay, sorry. There was a 4 as well. Sorry. There was a 4 here, right? I missed this 4. That is what I was thinking. What am I doing the wrong? So this 4 will get multiplied. So basically, right, it will be roughly equals to 180. Okay. So this will be 180 whole square. So ultimately, I will have a 180 whole square here. So basically, I missed this thing, so I have to multiply this by 16 actually. So this comes out with 2.037 Henry. Okay, this is the core self inductance, but they have asked me the overall self inductance. So overall self inductance will be, already I have derived the expression, it will be L core plus the leakage, right? So it will be equals to 2.0357 plus the leakage already they have given me as 0.16, right? So this will be 0.16. So ultimately the value comes out to be 2.195 or 196 Henry. Okay, but they have asked in millihenry. Remember, they have asked in millihenry. Okay, millihenry. So I will write down still more decimal places actually. So this is 19575. So this is Henry. Millihenry, this will be 2195.7 millihenry. Okay, and trust me, okay, This is the answer, that is fine. But if you go and see any PYQ book, okay, you go and see any PYQ book, how they have solved this question. This is like 2022 or 2023 question, I don't remember, 2022 or 2023 question. They write, you will not get an idea at all. You will not get an idea. Any PYQ book you see, any PYQ book, they will never solve using basics. So I have actually told you the basics. Okay, trust me, the dropper students will understand actually, because they will know, they will see that in PYQ they never understood the solution. Okay, they never understood the solution because they had not explained it like this. They just simply used some formula, random formula, okay, adding the mutual inductance and the self inductance, that's it. So but I have proved to you with basics. So that is the difference in our class and in other classes. Okay, you can go any PYQ book, you see the solution, you will not be able to understand. This is some gate 2023 or 2022 problem, I don't remember. Okay, in transformer chapter. So yeah, now that was the all the questions. Now let's discuss about a bit about multiple winding. We have discussed a lot about multiple winding, but now we will discuss about basically the the equivalent circuit of multiple winding. So this we already know that if I have a dot here, right, for a single window, I will have a dot here, I will have a dot here. That we already know. The EMF per turn will be same. EMF per turn will also be same. That is basically the flux basically. Because I know flux is proportional to voltage by the number of turns. So flux is constant, flux is fixed as voltage and number of turns are fixed. So that's why EMF per turn will be same in all the windings. So V1 by N1 will be equals to V2 by N2 will be equals to V3 by N3. This will always follow no matter what. This will always follow no matter what. Okay, but current you have to balance the MMF. Okay, so one more thing I want to discuss for multiple winding transformer, that is the power. So if I have connected an input here, so there is no other source, right? No other source. So this will supply all the power. So the energy or the apparent power delivered by the source is V1 into I1 star conjugate. This should be equals to the apparent power absorbed by this impedance and apparent power absorbed by this impedance. What is the apparent power here? That is equals to V2 into I2 star, and apparent power in the tertiary winding, that will be equals to V3 into I3 star. Okay, so from here as well we can actually derive the MMF balance equation. So if I divide by V1 on both sides, this will be I1 star will be equals to V2 by V1 into I2 star plus V3 by V1 into I3 star. Okay, so V2 by V1 is just what? It is N2 by N1 and this is N3 by N1. Okay, so all these are complex. So what I can do, like, I hope you remember this property. If I have two complex number, let's say Z1, Z2, okay, and I add them and I take the whole conjugate, it will be like Z1 conjugate plus Z2 conjugate. Correct? Now if I do the reverse, I want to take the conjugate again. This will be Z1 plus Z2 because it is Z1 conjugate and Z1 of conjugate will be Z1 only. So same thing I will apply. I will apply conjugate on both sides. This will be I1 conjugate equals to V2 by V1 is N2 by N1 into I2, this conjugate is there, plus N3 by N1 into I3, this whole conjugate is there. Okay, so this will be equals to I1 equals to this N2 by N1 is just a constant number. This will be I2 conjugate of conjugate, that is I2 only, plus I3 conjugate of conjugate, that is I3 only. So from here as well you can see the MMF balance equation. Okay, there are many ways to prove a single thing. So this is also another way that you can use the MMF balance equation. Okay, got it. Now let's discuss a bit about the equivalent transformer. Okay, equivalent circuit of the transformer. So if I have this circuit, right, same, like we will follow the same thing only, whatever we have discussed, we will follow the same thing only. Okay, for two winding transformer, whatever we have discussed, we will just copy that concept. So here I know that my V1 of t is here. Okay, so I will have a V1 of t here, that is fine. Then the primary will have some winding resistance, will have some leakage reactance, then it will have core resistance and magnetizing reactance. So it is Xm. Okay. So this is the case. This is the case here. This is the magnetizing component of the current. Okay. What about the other side? So other side, right? If I'm not referring it, if I'm just not referring it, so this will be what? This will be again the winding resistance of the secondary winding and the leakage reactance of the secondary winding. Actually, this should be XL2, right? XL1, this will be XL2, and then the impedance is obviously there. I have not referred. I have not referred yet. Okay. So this is the basically E2, and this one is what? If I have enough space, so we'll just reduce the size. So this one will be my E1, and I will have a tertiary winding. So this will be like tertiary winding resistance R3 into J XL3. This will be Z3. Okay, and this is my like induced EMF E3. Okay, this is my induced EMF E3. Okay, so I got these values. Now I want to connect this circuit. How will I connect it? Very simple, right? Just referring concept. Just simple referring concept. So if I want to connect these three circuits, here it is basically whatever I have drawn, the same thing is here. Okay, without referring. Now how to connect it? Simply, right? These points will be connected. Dot will be with dot. That I hope you remember, right? How to connect it. So I have connected it here. So everything is referred. Everything is referred. So I2 dash will be what? I2 dash. If I want to write the I2 dash, I2 dash will be equals to I2 into N2 divided by N1. Referring, you know, right? I will not explain you referring. Referring, you know. Okay. What will be I3 dash? I3 dash will be I3 into N3 divided by N1. Okay. What will be the R2 dash? Very simple, right? R2 dash will be N1 divided by N2 whole square into R2. Same for R3. Okay. I will not repeat. So, and this load also will be referred, right? So this will be the load Z2, ZL2 or whatever you want to write, Z2. This will be the load Z3. All this will be referred, and this point will be all in parallel. Okay. So this will be the impedance E1 here. This will be E2 dash referred to the primary. This will be V2 dash. This will be E3 dash referred to the primary. This will be V3 dash. So this much only I wanted to explain. That's it. Okay. That's the theory part of multiple winding transformer. So let's do few questions on this. So I want you to try out these questions. Pause the video. Try this first question and this second question. Okay, then I will solve these questions. Not that difficult. These are easy questions only. Mostly these are easy questions only. Okay, so let's solve this question. So this is a very old question, K 2003 IIT Madras. So figure shows an ideal 3-winding transformer 1, 2, 3 are wound on the same core as shown, N1, N2, N3. So N1 into N3 are turns ratio as given. So N1 equals to 4, N2 equals to 2 and N3 equals to 1. These are the turns ratio. So a resistor of 10 ohm is connected across a winding 2. So 10 ohm resistor is connected across winding 2. A capacitor of reactance 2.5 is connected across winding 3. Okay. So winding 1 is connected across a 400 volt supply. If the supply voltage phasor V1 is this, the supply current phasor I1 will be what? If supply voltage phasor V1 is given as this, what will be the supply current phasor? Basically they are asking me what will be the current value. That is what they are asking. So multiple ways to go about this problem. You can use the MMF balance equation. Okay, you can use the MMF balance equation, or you can refer this whole circuit in the primary, whichever one is suitable to you. Okay, so I will give you the homework. What is the homework? Okay, let's do it only. Anyways, I will do it anyways. Okay, so they have told me that this is an ideal 3-winding transformer. So there is no leakage reactance. There is no winding resistance. Okay. Yes. Okay. And there is also no magnetizing current actually, because it is an ideal transformer. So yeah, that is also not given. So like this circuit is very easy. This circuit is very simple, right? There is no core loss, magnetizing reactance, nothing is there. So basically the circuit gets converted like this, that I have this supply here, V1 is here, okay, and at the 2 points I can refer this R to the primary. So this will be 10 into N1 divided by N2 whole square. So 4 divided by 2 whole square. And if I want to refer this capacitor in the primary, this will be Xc into N1 divided by N3 whole square. So this will be minus of J. Xc is how much value? Xc is 2.5, right? So minus of J 2.5, and it is N1 divided by N3 whole square. Okay, N1 divided by N3 whole square. Okay. Yeah, okay. So they are just asking me the primary current I1. Very easy to calculate, right? Not that difficult. So current I1 will be basically equals to V1 is already given to me, that is V1 supply is 400 angle 0. So it will be 400 angle 0 divided by the resistance, that is this is 40 plus this is what value, okay, 400 divided by 40 plus 400 angle 0 divided by minus of J. So this will be 16 into 2.5. 16 into 2.5 is 16 into 2.5. This is also 40. 40 of minus of J, that is 40 of minus of 90 degrees. So this will come out to be 10 plus J10. This much simple question. This is a very simple question. 10 plus J10, which is present in the option C. So option C will be correct for this question. 10 plus J10 will be the answer for this question. Okay, very simple. Like you can, this is the method 1 referring. Okay, or you can apply the method 2. What is the method 2? Method 2 is simply MMF balance. So N1 into I1 will be equals to N2 into I2. So this is MMF balance plus N3 into I3. Okay, you can apply this and you will be able to find out the same answer. Let's now solve the last question of today's lecture. So we have a 3 winding transformer. The turns ratio primary, secondary, tertiary is given like this. Lagging current 50 ampere at the secondary and 60 ampere at the tertiary winding. Find the power factor of the primary current. So again you can apply the MMF balance equation, right? So so the current in the secondary I2 is 50 ampere with lagging. So I2 is lagging. So if I assume the reference to be the voltage, okay, V1 voltage as reference, so it is lagging. So current will lag the voltage. So I will have negative of cos inverse of 0.8. Cos inverse of 0.8 is 36.86. If you remember, right, cos inverse of 0.8 is 36.86. Okay, minus 36.86. And my I, so in rectangular format, what is this? So this will be 50 cos of 0.8. So this will be basically 40 minus J30. Okay, this will be the value 40 minus J30. Yes. And what about I3? So I3 is 60 amperes with power factor of 0.6. So this will be in rectangular format. This will be 60 cos of 60 into 0.6, that is 36. And this is actually, okay, they have not mentioned whether it is lagging already. Lagging currents, okay, both are lagging currents because it is said here currents, lagging currents, okay, multiple. So both are lagging. This is also lagging, this is also lagging. So it will be minus of J into 0.8, basically 0.8 into 60. So I hope you know, right, basic things like cos, if cos phi is 0.6, sin phi will be 0.8. So 0.8 into 60 will give me 48. Okay, and then I will simply apply the MMF balance equation. So MMF balance equation, I will apply MMF balance equation. it will be N1 into I1 will be equals to N2 into I2 plus N3 into I3. Okay, so N1 into I1 will be, N1 is 20, I1 I have to find out, N2 is 4, I2 is given as 40 minus J30 plus this is 1 into 36 minus J48. So I1 will be 1 by 5 basically. So if I take 10 common here, right, so this will be 40 divided by 20, so this will be 2 into 4 plus J3, 4 minus J3 actually. And can I take anything common here? I can take common here 6. Anything other than 6? No, I guess I will not be able to take anything else common. So this will be 1.8 minus J 2.4. So the values here, right, will be equals to, so my I1 will be actually 8 plus 1.8, so 9.8 minus 6 and minus 2.4, so this will be minus 8.4. Okay, so from here, like they're asking me the primary current and the power factor. So power factor will be lagging only. So magnitude of the current I1 will be equals to, if I convert this into the polar format, so this will be 9.8 whole square plus 8.4 whole square, so this will be 12.9. Angle will be what? Angle will be 8.4 divided by 9.8 of tan inverse. So this will be minus of 40. So what is the power factor basically? Cos of this angle, right? Cos of this angle will be the power factor. So power factor will be 0.76 lag because angle is negative. It is lagging with respect to the voltage, and current value will be this 12.9 amperes. So this will be the answer of this question. So these kind of simple questions mainly come. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button. Make sure to comment down below if all the concepts were clear. That question, right, that self inductance questions is one of the best question. Okay. So yeah, I hope you have enjoyed this lecture. I will see you in the next lecture. Until then, happy learning.